Okay, good morning, everyone. Sorry for the delay starting up today. So we're going to talk about some very different approaches to clustering now based on matrix structure. So the main idea is to exploit the low rank property that we find in this term document matrix. And in particular, we would like to factorize a matrix into a product of a tall and wide matrix. And so here's our term document matrix. And we're going to factor it into a matrix. Of course, we need to match the n documents here. But then we're going to choose to only have a rank of capital R. And in doing so, here's our singular value decomposition approximation. Basically, this is like what we did for PCA. So we have US V transpose. So there's going to be R columns here. So you can think of this first matrix as showing you the relationship between the different documents and different topics. And then this matrix shows you the relationship between the different terms and the different topics. And then the singular values in here tell you essentially how much each topic is weighted in the overall term document matrix. Okay, so this is basically PCA applied to the term document matrix. And as you know, PCA minimizes the RSS between the true term document matrix and its approximation x hat, where that approximation is given by this low rank thing here. So there's another option, which is non-negative matrix factorization. So this also factors X into something that has tall matrix, number of documents by number of topics, and then another matrix, which is number of topics by number of terms. The difference is that when we do NMF, we minimize RSS under the constraint of non-negative factor matrices. So all the terms in W and all the terms in H will be non-negative. So that's the difference in terms of the formulation, but it has a huge effect on what happens, as we'll see. All right, so let's talk about each of these in a little bit more detail. Okay, so the first one where we apply PCA, when we do this to the term document matrix, it is called latent semantic analysis. It's just the name that it's given, and there's a whole Wikipedia page on this, and this is a very well-known technique. It has been used quite a bit. So again, this is just the picture from the previous page. As we know, to do PCA, we can take the matrix, we can apply singular value decomposition. So if we apply the economy, SVD, then we get an equality. Right? X equals this exactly. Nothing is lost. And here we need that R is the rank of the matrix. But typically, we have many fewer topics than the rank, and so we might instead choose to do an approximation. We approximate it using capital R, which is much smaller than the little r. So that's the idea. maybe I should, oops. I usually do this with green font, so I'll do that. Yes. Okay, so that's the key point. It's like PCA, except it's applied to a term document matrix. And when you do this, you naturally get a decomposition which tells you how documents relate to topics, how terms relate to topics. So for example, let's say I had one particular document I was interested in analyzing. That document would correspond to some row of my X matrix, right? So then on the right, I would say, okay, that's approximated by this row of the U matrix, and so when people want to do like a document analysis where they say, tell me which topics are represented in a given document, they'll essentially look at these numbers here, and they'll look for, maybe if you want to find the topic most associated with the document, you'll just look for the largest number in this row. So they're using PCA to squeeze down a matrix which is going to be huge into this more efficient representation. But not only that, is you can see the structure of the documents in terms of these topics. Similarly, if you wanted to know for a given word, maybe you said for a given word, maybe this word, how is that word represented across topics? You could look at the corresponding row in V transpose or the corresponding column in V. So these are the common things that are done with latent semantic analysis. If you want to know the relationship between two different documents, in that case, what you could do is you could take two rows of here and you could do their inner product. Maybe you would normalize it by the norm of each row. That's one approach, but these are very long vectors, so instead you might choose to just take these two corresponding rows here and take their inner product. So this is another common thing they do with latent semantic analysis. Okay, so this is like just one option we have. Yeah, just a little bit more about that. Once you do this decomposition here, you can then write it like this if you want. So UK is the kth column of this U matrix. VK transpose is the kth row of this VR transpose. And you can think of these U's as the principal document vectors, the V's the principal term vectors, and these S's would be the weights of, SK is the weight of the kth topic in this corpus of documents. Okay, so this is certainly one way to go. But when we do this, we find that there's a couple of things that are specific about PCA that we inherit here, which are not necessarily what we want. So remember that the principal components are going to be orthogonal to each other. So these columns here. That's not necessarily particularly useful in this topic modeling, but more specifically, it implies that the values in those matrices can be negative. They can be positive, they can be negative. It can be zero, they're probably not going to be zero with high probability, but probably about half of them will be negative. So that's kind of an issue because it's not clear how exactly to interpret those negative values when we do the decomposition. So let me put a little frowny face there. Okay. So let's do an experiment now. We have our data set. We can try this PCA approach on the data. And this is what we get. So when we look at principal component 0 and we look at the words, or the terms, basically what we're doing here is we're looking at V0. This has all of our terms in it, and then we can rank them, print them out, and we don't really see any pattern here. We can look at the next one. We see things that seem to be religion or atheism, and then we have things that seem to be, I don't know, maybe computer graphics, DOS, and so on. And the next one, same thing. We see things that maybe have to do with space, things that have to do with computers, and same thing for all of them. So we don't really see any clustering. We can also look at the confusion matrix that we printed before. If you remember what this matrix shows, is this is the true topics versus the clusters. And ideally, these numbers in each column would be, there'd be like one large number and the rest small, but we don't see that. The numbers are quite evenly distributed across columns. So essentially, confusion matrix looks bad. The components don't look well clustered. So even though LSA is kind of a well-known technique and it's used for the analysis of these structures, it doesn't really seem to work well for topic modeling for clustering. Okay, so what about this other approach, non-negative matrix factorization? So on the surface, it's very similar. So it's doing something where, again, we're minimizing RSS. The only difference is that now we're forcing the matrices in our product to be non-negative. So that's what the little subscript plus means. So of course, if we add this extra constraint that we didn't have in PCA, we don't expect to do as well in minimizing RSS. So in particular, we expect the approximation error to be larger. And it is if you checked it. However, the good thing is that the coefficients in these matrices are interpretable since they're positive numbers. The larger they are, that should mean that they're more relevant. So for example, if we do this thing again, where I want to look at one particular document, and I want to say, how does that document appear across different topics? I can look at the corresponding row in W, and now I know that 0 would mean it doesn't show up in a given topic, and a larger number means it shows up more in that topic. PCA was confusing because you can have negative values. What does it mean if it's negative? Like, can't really contribute negatively to a topic. Okay, so this is the difference between non-negative matrix factorization and PCA in terms of their definitions. And so now let's apply this to our data set. And immediately you can see very good clustering. So the first one has all these religious words. The second one has all these computer graphics type words. The next one has all these space or space words. And then the last one is a lot of atheism or religion words. Similarly, we can look at the confusion matrix. When we look at the first column, we see a very nice grouping of religion or atheism and religion. Now you could argue that, well, maybe these two are so mixed that it's really impossible to separate them according to the ground truth. But at least this approach is filtering out graphics in space. Next column, you can see it's pulling out the graphics ones, 92. Next one, pulling out the space ones. And finally, we see, again, a combination of these two, but weighted more towards atheism, less towards religion. So overall, you could say the confusion matrix looks pretty good. You could argue it looks better than with k-means, because in k-means, if you remember, the second one was sort of all mixed up. It didn't really correspond to anything. This one, all four clusters make sense. Okay, so it seems to be a very useful method. And in fact, it is. So here's another view of it as to how it's different than PCA. And this brings us back to the faces example that we saw in the previous unit when we first applied PCA as a way of deconstructing or compressing faces. So the pictures on the right, maybe we'll do PCA because it's familiar to us. So down here in PCA, what you have is a face, and and these are all the little eigenfaces. Each one of these is an eigenface, and then each one of these is the scalar weight that you apply to those eigenfaces. Actually, this very first one is just the mean, and then all the rest are the eigenfaces. So this is saying, like, to construct that face, positive numbers are black, negative numbers are red, white is 0. So you take a large positive number, multiply it by this mean, and then you take, all these other numbers, you multiply them multiply their eigenface according to those numbers, and then you add them all up, and you get this. So overall, you get a decent approximation. So the NMF picture works in exactly the same way. You don't have a mean vector in that case. You just have all these, we wouldn't want to call them eigenfaces anymore, but these are our components, and these are the weights, and everything is positive. All these numbers are non-negative. All these numbers are non-negative. All these are non-negative. And together, they give you this. What's very interesting is that when you look at the components in NMF, they give you what's called a parts-based representation. So you can see here like eyebrows or a mouth part, maybe like a shadow on the side of the nose, and so on. Here it kind of looks like you see almost a whole face. So it just shows you that the way that it decomposes things is very different than PCA. You're really building a face using non-negative contributions of a bunch of parts. As you come down to PCA, and you can see the red means negativity. So you have these pictures, which a lot of them are, a few of them are interpretable, but a lot of them are very hard to interpret. They don't really look too much like faces. They have positives and negatives, and then here you're weighting them by positives and negatives and so on. So even though at the end of the day, it actually will give you a better, in terms of RSS approximation than this, the building blocks are fundamentally different. And in certain applications, it's really advantageous to have these sorts of building blocks, as we saw with clustering. Okay, so this NMF is a very well-known approach, and actually in this sort of context of deconstructing real-world signals, and often this is a better solution than PCA. So here's a few similarities and differences between them. So we have NMF, PCA. Okay, so both of them are low-rank approximations of a matrix. NMF is designed for a non-negative x, so that's important. If the matrix you start with has negative values, you cannot apply NMF to it, or you shouldn't. But in this case, our x is positive, and so we can. Meanwhile, PCA can be performed on any x, even a complex valued one. Okay, NMF gives non-negative factors, while in the PCA decomposition, the factors can have negative values. NMF gives non-orthogonal matrices, whereas PCA gives orthogonal matrices. Let's see, my pen may have died. Let me charge it a little bit. NMF encourages sparse factors. So by that, look back over here, you can see in the top middle figure, you can see a lot of zeros, a lot of white. So those components are sparse. Whereas in PCA, even though there are some whitish values, if you look closely, they wouldn't be exactly zero. What else? Okay, so now some of the difficulties with NMF. It's non-unique, while PCA does have a unique solution. And the NMF optimization problem is non-convex, so your solvers can get stuck in local minima, whereas in PCA, we have a closed form solution. And so there's no problem in computing those. So these are some of the advantages and disadvantages of NMF versus PCA. There's a lot of other fun applications of NMF. Let me just briefly tell you about one, which is called the Netflix problem. So in the Netflix problem, Netflix, about 10 years ago, they sponsored a contest which they wanted to try to improve their algorithms. So in Netflix, you have a problem where you have many users and many movies. And so when you think about any given user, that user has only seen a subset of all the movies that are out there, or that Netflix has, right? Very small subset. And when you think about so in other words, given user, only a few of those movies are rated. Similarly, for a given movie, only a subset of your users has seen it. So essentially, what you have is they have data where they have values. Maybe they have like stars from 1 through 5. So maybe they have I'm just going to make up something like this. So they have a matrix with recommendations, but their matrix is very sparsely populated. There's a lot of missing values. Like by far, most of the values in there are missing. So the question is, their objective is to fill in all the space, because they want to be able to put in numbers everywhere so that for a given user, they can make recommendations on movies, right? Or you could say maybe for a given movie, they want to know which users they should market that to, put it in advertisements and so on. So they want to complete this matrix. So this is called a matrix completion problem. And matrix completion is one of the fundamental problems in recommender systems. So this doesn't just apply to movies and users, it applies to products and customers for Amazon and things like that. So it's where you have sparse data and you want to fill the rest so that you can use it in some business application or many other applications. So if you take this matrix and you just basically fill in zeros for all these missing values, and then you apply non-negative matrix factorization to that zero-filled matrix, you actually get really good factors, which what you're doing here is you're exploiting the idea that there's really only a few kinds of humans that have few preferences. Like, even though you might have 1 million users in the database, there's not, at the end, 1 million really different users. There's people that like these kind of movies, people that like these kind of movies, and so on. And so you can build an approximation like this, where this is a tall and skinny matrix, where you have, essentially just a few kinds of users. I don't know how many, maybe 10 or something. Similarly with movies, you could say, even though I have millions of movies in my catalog, there's really different categories of movies, and that's, there's not too many. Maybe there's 10 or 20 categories of movies. Fundamentally, and all movies can be pretty well grouped into those. And at the end of the day, actually, I think I might have drawn that wrong. Sorry, yeah. So this is essentially what you get. These topics now, in this context, become the types of movies and the types of users, one and the same. So this was when Netflix proposed this, roughly 10 years ago or so. Matrix completion, or non-negative matrix factorization, or low-rank techniques for matrix completion, somewhat surprisingly, gave almost the top solution in this contest, like a very simple algorithm. And people came up with all these much more complicated algorithms to solve it, but really non-negative matrix factorization, matrix completion was what worked well. So it's a really powerful technique. All right. Any questions on any of this? All right. So we have one more type of clustering approach to talk about, which is based on Gaussian mixture models. And this has we'll see it's much closer in spirit to k-means, but it's founded more on a probabilistic way of thinking about things. And then in talking about this, when we try to fit this model, we're going to learn about another very important technique called expectation maximization. Okay, so this is just sort of going back to basics. I think you've all seen this before, but one of the most important of all the distributions that we talk about in statistics is the multivariate Gaussian. So this is just a Gaussian with more than one variable, where you say that all the different variables in this random vector x are what we call jointly Gaussian. So they're individually Gaussian, but then they're also Gaussian with respect to each other. And what this means essentially is that they belong, x is generated by this distribution. So the distribution, the PDF here, has two parts. The more important part, I would say, is this one. So you have e, and then to a power of a negative quadratic form. So here you have x minus the mean vector on both sides, and in the middle you have the inverse covariance matrix. So this is really, I'd say, the interesting part. Now you do need that if you integrate this over all x, that has to equal 1, and that's what this scale factor does. This scale factor makes sure that everything is normalized so that it's a valid probability. And when talking about this, we'll just use this shorthand notation. So x is the variable of the PDF, mu is the mean vector, q is the covariance matrix. Okay. So there's different ways to visualize this. One way to visualize it is to generate a bunch of x from that distribution and make a scatter plot. And if you do, then you get something like this. And so the center of this shape is going to be the mean. And the shape could be circular, or it could be stretched a little bit in a particular direction. And if it's stretched in a direction and you want to know what this direction is, all you need to do is take an eigendecomposition of Q. And now you have your eigenvectors and your eigenvalues. And it turns out that the eigenvectors, which, remember, these are orthogonal in this context because this Q is a positive definite and symmetric matrix. So these are going to be orthogonal. And these lambdas are going to be non-negative. So the columns of V are exactly the directions, the principal axes of this shape. And this shape ends up being an ellipse. So you have these principal axes. And if you want to know how much they're stretched, you look at the 1 over the square root of the eigenvalue. That tells you how much it's stretched. You can also look at this without generating points. You just, let's say, look at the level sets, or here we have like a mesh plot where we have, these are the level sets. These guys are all ellipses, and those ellipses are the same kind of ellipse that you see here. So again, you can look at the principal axes of those ellipses and look at how much the ellipse is stretched out, and that's going to be given by the eigenvalues and eigenvectors. Okay, so there's just another way that we see these eigenvalues, eigenvectors are important in statistics. Okay, so when you look at this plot here, this is similar to sometimes the type of clusters that you see in some of these toy problems, right? Here's another plot. We saw something very similar to this towards the beginning of this unit. We had a data set in 2 dimensions. And if we're given this and we're asked to cluster this data set, then you say, well, okay, these points are all close together. These points are all close together. So that seems to be a good clustering. So the question is, how can we describe this in terms of probabilities? Is there a probabilistic formulation for that idea? And the answer is yes. It's based on thinking of each one of these as a Gaussian. So that's a Gaussian, multivariate Gaussian. This is another multivariate Gaussian. They do have different means, as you can see. They have different centers. They can also have different covariances. We could also tilt them and so on. But then, so here you can see this is the Gaussian mixture model, which is what we're working towards here. So here we have the different means. So little k is indexing through those mixture components. We have the different means, different covariances. But we also want to have the possibility of having more points in one of these and fewer points in another. So that's what these weights are helping us do. Now there's some constraints. The weights have to be non-negative. Otherwise, we wouldn't have a valid PDF. We'd have negative probabilities. Also, the weights have to sum to 1 so that when we integrate this, that integrates to 1. Okay. So that's the idea. This is a probability density function that describes the presence of multiple Gaussians simultaneously in your data with different means and different covariance. And once we have this probabilistic representation, then you can see it's relatively straightforward to cluster our data. We'll go through the details, but essentially we want to find, if someone gives us a new vector x, we want to determine which GMM component k it's most likely to correspond to. Okay, so to do this, it helps a little bit to develop what's called the hierarchical form of this GMM, which we'll talk about on the next page. But are there any questions before we go further? Okay. All right, so essentially we would like to understand this weight component better, or maybe in a different way. So this is going to be, we can think of this now as a 2-stage approach to generating a random vector x. So in other words, let's say that I wanted to generate samples as we have them here. We want to plot a scatter plot. So how do I do this from here? If it was a Gaussian alone, we know how to do that, right? That's pretty straightforward. Or at least you could easily do this, even if you didn't know exactly how to do it. You could do it in Python. But what if I want to generate things from this distribution? It's no longer Gaussian, it's this Gaussian mixture. So how do we do that? Basically, we can think about this as a two-stage approach. First, we want to draw a realization of a random variable that tells us which component the data is coming from. In other words, I'm going to, in this case, maybe flip a coin to tell me is it coming from here or here. Maybe it's a weighted coin. Once I know that it's coming from one of these, now it's just a matter of generating a Gaussian sample, which is pretty straightforward. Okay, so again, 2 steps. First step is draw the component index kappa. Second is draw the vector x according to the PDF that's Gaussian that depends on kappa. Okay, and the way that the first step works is in order to draw this, we just think about having the probability mass function that's given by the sequence of gammas. The gammas are, if you remember this, these ones. Remember that they're non-negative and they sum to 1, so they're a valid probability mass function. So given this probability mass function, that defines a discrete random variable that takes on values 1 through k. And so we can draw from that distribution. And in particular, the probability that we draw 1 would be gamma 1. The probability we draw capital K would be gamma capital K, and so on. So, if we have 2, that's like doing a coin flip. Otherwise, it's a little more general. Once we know what that kappa is, then we just focus on the PDF, the Gaussian PDF for that kappa, and we draw that random variable. So in terms of the math, you could say the probability that kappa equals some value k is gamma k, and the probability of x given the kappa is k is this Gaussian with mean mu k and qk as the covariance. Does that make sense, the overall idea? So here's a little proof of why we can do this. So we start with px, and then we use the law of total probability, which says essentially if you add one more random variable to this distribution, and then you average out that second random variable here, that it brings you back to the first one. So this is the law of total probability. The second step is to rewrite this joint probability in terms of the conditional probability times the marginal. So this is essentially just the definition of conditional probability rearranged a little bit. And then the last step is we're just plugging in, we're just using a notation, gamma k for this, and this is our Gaussian in this case. So this gets us back to what we had in the previous page. And so you can see that, that drawing things in this 2-stage approach, you get back exactly the Gaussian mixture model from the previous page. The key point is that when you draw these kappas, they are coming from a probability mass function defined by the gamma k's. Okay. All right, so again, first draw kappa, then draw x given kappa. So there's a special name for when you do this sort of things, these sort of things. It's called using hidden variables. The variable kappa is hidden because, like, when you come back to our original way of writing the Gaussian mixture model, there is no kappa, right? There's no kappa there at all. It's hidden, it's kind of implicit. And in fact, it's not the only way to to inject a hidden variable. There's other ways you could come up with hidden variables in here. It's just one of many ways, but it's sort of a natural way, at least for this problem. Okay, so now that we have this kappa identified, this, and basically it's like, this is sort of the, maybe our new way of thinking about things here. Now that we have this kappa identified, when we want to do clustering, it's all about determining the most likely kappa for a given X vector. Okay, so here's our Gaussian mixture model from the previous page. And if somebody gives us a new vector X and asks us to cluster it, essentially they're asking which of those Gaussians in the mixture does it correspond to? It's essentially saying, find the most probable component index kappa associated with that X. So this is this is essentially this map problem that we've seen before. So we want to find so down here, this is essentially what we want to do. So this is this quantity. What's the probability that kappa equals k, where k is some hypothesized index, given a vector x? I just want to compute this for all the different k, search over them, find the largest k, or largest kappa, and that will be my clustering answer. So this is this map idea, maximum a posteriori, that we saw back in Unit 4. Okay, so then the next question is, well, how exactly do we compute this quantity? So this is a quantity, probability kappa given x, is not something we've seen before. We have seen probability x given kappa. We've seen probability kappa. We haven't seen probability kappa given x. So this is a perfect time to employ Bayes' rule to solve this problem. So Bayes' rule allows us to essentially swap the order here. And once we can swap it, we can bring in the things we know. So this is how Bayes' rule works. Here's where we swap them. And then we have to compensate. So probability x given kappa times probability kappa divided by probability of x. Is everybody with me so far? So we know this, probability x given kappa, that's our Gaussian. Probability kappa equals k, that's gamma k. And what about probability of x? So probability of x, as you can see, is the sum over the gamma k's times the Gaussians. So that gives us this. And just to avoid confusion, because we're naming this variable k over here, I don't want to use it down here in the subscript, so I'm just going to call everything k prime, just to avoid confusing it with this one in the numerator, which is tied to this one on the left side. Okay, so if somebody gives you a vector x and you compute this quantity for each k, you have a probability mass function that tells you the probabilities that x is associated with this and any other clusters you might have. So for example, if I had my x over here, I would assume that the probability that's associated with this cluster is much larger than the probability associated with this, right? Because the probability falls off quickly as you go away from those clusters. If I had an x here, those probabilities would be close together. Both of them would be maybe close to 0.5. But that's what we're computing. We're computing that vector of probabilities here. So we can call that a soft assignment. Now, if someone says, I don't really want all that information, I just want you to tell me the closest, the most probable cluster, that would be the hard assignment. So you take that vector and you find the index of the maximum component, and that gives you one number. So if I'm over here, it would tell me this is the closest cluster. If I'm over here, it would tell me this is the closest cluster, and so on. So that's essentially, yes, that's how we do it.
Is this similar to the softmax function we learned, where you sum over exponentials above and get an exponential?
It's a little bit related to it, but it's similar, but I wouldn't say it's the same. In that case, you had the model, instead of a Gaussian, you had it's like an e to it was something that was linear in z, right? Whereas here it's quadratic. So it's reminiscent of it, but it's a bit different. But what's similar in that case in the softmax, you also had a PMF on the left. We have a PMF on the left here. So yeah, it's similar in spirit, but the details differ. Okay, so here's a summary. GMM-based clustering. So the first thing, which we actually haven't talked about yet, is we need to fit our Gaussian mixture model parameters, all our gammas, mu's, and q's, to our data set. Once we fit all those numbers, then we compute this for all the i's in our data set, all the samples, as well as all the k's. For each I and each k, compute this. And finally, once we have that for each I, we look over the vector of different k's for each I, you find the maximum index in that vector, and you report that. Okay, so that's basically saying here were the hard what do we call these? The hard assignments are given by the color. So all these light blue points have a hard assignment associated with this color. All these red points have a hard assignment associated with this. If we were plotting soft assignments, you would see colors that were between red and blue, but here these are the hard ones, so it's either red or blue. Okay, so that's how we can do clustering. Now the next part, which we won't talk about today, we'll talk about it on Wednesday, is how do we fit the GMM parameters. So our go-to approach is to use maximum likelihood estimation. So if we call all this stuff theta, we want to find the theta that maximizes the likelihood, probability of x given theta, or similarly the log likelihood. Now if you plug in our expression px given theta in here, this is what it is. It's the sum of the weighted Gaussians. And so here, as always, we assume IID xi, so here's the sum from all our samples. The problem is, this is a non-convex optimization problem. Difficult to solve, so we can't take this direct approach. It has a lot of local minima, so on, so we have to be careful how we optimize it. So we're going to use a famous algorithm called the expectation maximization algorithm. And that will be the next topic, and the last topic, actually, to talk about in the course. And so we should be able to finish that up in one lecture. And so we'll just have one more lecture on Wednesday, and then we'll be done with our lectures. Any other questions on anything regarding Gaussian mixture model clustering or anything? Okay, as we'll see, we'll do a comparison later between GMM-based clustering and k-means clustering. We'll see there's a lot of similarities. GMM-based clustering is like a soft probabilistic approach. K-means clustering is sort of a more of a deterministic, hard clustering approach. But they are, as we'll see when we look at the algorithm, they're similar in spirit. All right. Well, if there's no questions, then that's it for today. And I'll see you guys on Wednesday.